So we've seen then that there was an overwhelming amount of both observational and theoretical evidence that light actually does travel as a wave, but there were a few problems: the black body radiation problem, the existence of spectral lines, the details of the photoelectric effect that didn't quite fit into the picture of light as waves. And in trying to solve that, the German physicist Max Planck in the year 1900, he did something similar to what Kepler had done in trying to figure out planetary motions. Remember that Kepler studied the orbital data that Brahe had discovered about Mars, and he kept trying to fit it into a heliocentric model, and nothing worked. And finally, in desperation, he said, what if planets don't move the way in uniform circular motion the way everybody had believed? What if the orbits were actually ellipses? Well, Max Planck did something similar. In order to explain the black body problem, he proposed the quantum hypothesis. And what he said is that, what if we consider light, in spite of the evidence, in spite of Maxwell's equations, what if we consider that light travels as particles rather than as waves? He named these particles quanta. The singular is a quantum, same place that we get the word quantify and quantity from. And he said, what if we apply this picture to the black body problem? And what he found was that it actually explained the actual black body observations perfectly, as long as he included in his calculations a very, very specific number for a constant. Very specific. That number is 6.626 times 10 to the negative 34 joule seconds. This number is now known as Planck's constant, and it's actually related to the smallest possible particle or quantum of energy. Now, this idea ran so contrary to most of the observations and Maxwell's equations that Planck himself didn't believe it. He thought that it was a useful way to do calculations for black body radiation, but he didn't actually believe that this was the way light really was. So he actually thought of quantum hypothesis as being pragmatically true, but he didn't accept that it was correspondently true. The road to accepting this as correspondently true lay with another scientist that we'll meet in a moment. But in the meantime, let me give you a little analogy so that you understand exactly what the quantification means. A good analogy is money. Money is actually quantized, although we may dream of having any amount of money possible. In fact, we can't. We're limited to certain amounts of money because money actually comes in packets that are actually multiples of some smallest packet. That packet is the penny. And so you can have, say, $712.34 or $712.35, but you can never have $712.34 or $712.35 because the smallest possible packet of money is 1 penny, 1 cent. And quantum theory suggests the same thing about energy, that energy comes in packets and the smallest packet is related to Planck's constant. Now, how did we get to starting to take this as something other than pragmatic truth just to explain one problem? Well, that happened when Einstein, who, remember, had taken Maxwell's equations seriously, and that led him to develop general relativity and special relativity. In the same year that he actually published special relativity, he also made another amazing calculation, he applied Planck's quantum hypothesis to the photoelectric effect to see whether that would also explain that phenomenon. And in fact, what he showed was that treating light like particles matched theory perfectly with observations as long as he included a very specific number in his calculations. You can probably guess what that number is. It's Planck's constant, 6.626 times 10 to the 34 joule seconds. Well, now, quantum hypothesis is well on the way to becoming quantum theory because it's done something amazing. An idea that was developed to explain one problem, black body radiation, turned out when it was applied to an apparently completely different problem, the photoelectric effect, gave a perfect answer. So now quantum hypothesis was taken much more seriously, and in fact, Einstein won a Nobel Prize for this. There's a bit of irony here that he won his Nobel Prize for confirming someone else's idea. He never actually won a Nobel Prize for either special or general relativity, the thing he's famous for today. Finally, quantum hypothesis really became quantum theory in 1913 when Danish physicist Niels Bohr applied quantum theory to another problem, an apparently unrelated problem, and that was the structure of the atom. What if the energy that electrons have in orbit around nuclei is actually quantized? What he ended up finding was that this actually showed that electrons must be found in energy levels, and it actually explained the existence and the location of spectral lines, at least for hydrogen, if, you probably see this coming, if he included a very specific number in his calculations, and that was, once again, Planck's constant. So now the same number and the same idea show up in three different phenomena, and scientists have to accept that this is telling us something real about energy. How does this explain energy levels? How does it indicate that electrons must be in energy levels? Well, because electrons circle the nucleus, and how far they circle from the nucleus is going to be dependent on their energy. The more energy they have, the faster they're going to move and the further away they will be from the nucleus. And since energy is quantized, the electrons can only have certain energies and therefore can only be certain distances from the nucleus. So imagine an electron with, say, the minimum amount of energy, 1 quantum of energy. Well, that's going to give it a speed that's going to put it at a particular distance from the nucleus, and we call that the first energy level. If you give an electron more energy, you can't give it 1.5 quanta, you can't give it 1 3/4 quanta, you have to give it a complete new quanta, like 2 pennies. The 2 quanta of energy will put it further away from the nucleus. It can't be anywhere in between here because that would involve having a fraction of a quantum, and that's not possible. 3 quanta of energy puts it at again a very specific location from the nucleus, what we call the third energy level or the third orbital. And so if energy is quantized, then electrons must be in energy levels. And this is the reason that one reason we believe this is because this idea of energy levels, quantized energy levels, actually explains spectral lines. Why do atoms absorb and emit energy? Because their electrons are actually taking that energy in, and that causes them to move further from the nucleus. But since energy is quantized, they can only absorb very specific amounts of energy, and therefore they can only make specific jumps between energy levels. So here, for example, imagine this electron in the first energy level. It absorbs a specific amount of energy, quantized energy. That amount of energy will correspond to a very specific wavelength, and that energy that's gone into the electron to bump it from the first to the second energy level shows up as a very specific dark line on the spectrum. Now, the electron, when it's in the second energy level, doesn't want to keep that energy, and so when it drops back down, it will re-emit energy, but since it's dropping between the same two specific energy levels, it will release exactly the same energy that it absorbed, and that will show up as a very specific spectral line on an emission spectrum. If the electron absorbs more energy, more quanta of energy, then it will make a different specific jump, maybe from the first to the third energy level, and that will be a different wavelength, and the drop back down will be again the same energy, releasing the same spectral line.